In this video, I'm going to conduct an analysis of covariance with sex as the independent variable, brain size as the dependent variable, and body size factor as the covariate. So now I'm introducing body size to determine whether there remains a significant difference between males and females on brain size. So go into Analyze, General Linear Model, Univariate, and put sex into the fixed factor, put brain size into the dependent variable box, and then you want body size factor as the covariate. And you can put more than one covariate if you want, but in this case we just have one. Now if you click on Options, you will want the descriptive statistics and effect size, but you're also going to want the estimated marginal means. So if you click on EM means, you'll get the option of sex and put in display means for. Now if you click on compare main effects, you're actually going to get exactly the same result associated with the ANCOVA. However, you'll additionally get 95% confidence intervals associated with the mean difference between males and females on the means that have been adjusted for the inclusion of the covariate. So I think it's actually useful to include this. Click Continue and click OK. So the first table is simply the between subjects factors, just telling me that the sample size is 60 and 40 for females and males respectively. And then the descriptive statistics, which are not adjusted for anything. These are just the ordinary observed descriptive statistics. It's the same thing you would get whether you did an analysis of covariance or not. So here we have males with 1.47 kilogram brain weight and females 1.27. Now in that ANOVA I did previously, I found that difference to be significant statistically. But now I've done the analysis of covariance, and I've included body size as a control factor in the analysis. Now the fact that it is not statistically significant is really ultimately irrelevant for the purposes of this analysis. The main thing is that it's included in the model, and now I can evaluate sex as an independent variable controlling for the effects of body size factor. And what we find is that the F value associated with the sex independent variable is 6.652, and with 1 and 97 degrees of freedom is statistically significant. Furthermore, the eta squared is estimated at 0.064, which is a very substantial drop from the original eta squared estimated in the ANOVA, which was 0.342. So a very substantial drop, but it's still statistically significant. The test of the difference between the means in brain weight between males and females is still statistically significant. Now I don't actually know what direction the means are just by looking at the F value. And who knows, including the covariate may have caused these means to crisscross. Females may now have a larger brain weight than males. I don't know. I have to look at the estimated marginal means. And that's the next table. So this is really important. And what we have here is that when you include body size factor into the model, the mean for females is 1.30 and the mean for males is 1.43 rounded. So the difference is still in favor of males, but it's not as big. If I subtract 1.428 minus 1.301, I get a difference of 0.127, which is clearly smaller than the difference between these two means. 1.474 minus 1.2706 is 0.203. So it's dropped. The magnitude of the difference has definitely dropped, and that's consistent with the notion that the males were also larger in body size, and it also happens to be the case that body size correlates with brain size. But the difference is still statistically significant in favor of males. And here are the 95% confidence intervals associated with the estimated marginal means, which include the body size factor correction. So males, at least based on these data, appear to have an advantage in overall brain weight controlling for body size, which may help explain why males and females overall have about the same level of intelligence. So on the one hand, females have some neurophysiological advantages, and males have at least one neurophysiological advantage, and it seems to about even out. Now in this other table, you will find the difference between the estimated marginal means, which is this mean minus this mean, and that includes the covariate. And you also get the 95% confidence interval associated with the difference between the estimated marginal means. And so it's ranges somewhere between 0.03 or 3 grams of brain weight to as high as 223 grams of brain weight. So it's a very large 95% confidence interval, which is consistent with the fact that the p-value was not terribly small, 0.011. Yes, it's less than 0.05, but it's not radically so. And consistently, the 95% confidence intervals associated with the adjusted means. These are also known as adjusted means. So that is how you can conduct an analysis of covariance. It's a very basic example with just one independent variable and two levels. In another video, I show you how to calculate an adjusted Cohen's d on the basis of the values in this table. I encourage you to check it out.